Hello everyone. I'm about to show you guys what I consider to be a very cool and useful way of multiplying numbers. The goal with this video is to kind of show you the machinery of this technique, and in a later video I will go into more detail as to why it works and why it will be useful beyond some of the usual techniques that are used. What you see here on the paper is basically a simple example of a perfect square that people usually memorize in times tables, 12 times 12. And I've done this using just different methods that most people are familiar with. This is kind of like the traditional one that's taught with the line at the bottom. Then you have the FOIL method, the first, outer, inner, last, here. And then you have this line method. I'm not going to go into any detail with either one of these methods because there's a lot of material available online about this. But with all these, they have their pluses and minuses. But they really kind of boil down to being just novelties, in my opinion. Just kind of algorithms and methods that you just learn and you do, and there's not much that you take with it beyond just multiplication. But with the technique that I'm about to show you, it utilizes a powerful tool in mathematics called a matrix. And once you understand the underlying structure of these matrices and how it applies to just basic multiplication, if you are a younger person just learning how to multiply, or even somebody who knows all these other techniques forwards and backwards, you'll be able to take what you learn from this technique I'm about to show you involving matrices and have a deeper understanding when you apply it to other fields, because matrices are tools that are used in a wide variety of STEM fields. And so that's why I think this is so important to get this out. I was inspired to formulate this technique by this line method. I like the geometrical appeal to it. I understand that there's another method involving arrays that is also kind of geometric. It's like boxy, and so that appealed to me, and I saw a lot of similarities between this and the structure of matrices. But the limitation with the lines is when you have large digits, like instead of using 12 times 12, if you had 99 times 99, there's a lot of lines you have to draw. So without further ado, I'll show you this matrices technique. And as I said, I haven't seen anybody else really doing this. So I believe I'm one of the few that actually put it out there. I mean, I haven't done extensive research to see if anybody else has put anything like this out. But usually, you know, when you think you have done something unique in mathematics, someone's probably done it a lot earlier. That's just how this thing works. But I would like to see this out and see people getting used to using it. And I think it will help them with their understanding and later in more advanced fields. So let's get started. So with this video, I'll just do a bunch of examples so you can kind of get used to the basic machinery. And we'll start with the example that I have here, 12 times 12. So the way this works is you start by breaking the number into two parts. So, you know, 12 can be written as a 10. So I'm going to put a 1 there in the 10 spot. And then it can be written as 2. So 12 consists of 10s and 1s, you know, because we count in base 10. So I'm going to write 12 like this. In a horizontal line with a 1 in a different place than the 2. All right, because that's the 10's place and that's the 1's place. There's 2 of the 1's. And so I'm multiplying it by another 12, but to distinguish that it's a different number, I'm going to write it vertically. So I'm going to have 1 separately here and 2 here. So that's the first step, is to write down the numbers in this way. 1 horizontal and 1 vertical. So that's the first step, is to just write them down. Okay. The next step is to build the matrix. So what is a matrix? It's just a fancy term. Basically describes numbers being ordered in a very specific way in columns and rows. And so how do we build this thing? This has nothing to do with Neo and Trinity. This is math here. But pretty cool though. Okay, so the way you build this matrix is you take the rows here. So when I write this horizontally, this number represents rows, and this other number represents columns. And so I'm just going to build this row by row. So this one says that it's the first row. So I'm just going to combine this one with the column. So I multiply 1 times 1, and I get 1 for my first entry for that row. Now when I multiply this by the next one, 2, 1 times 2, I get 2. And that's the end of this row because there's nothing else that I can mix with that 1. So I'm done. Now let's go to this guy. That's the second row. So 2 times 1, when I combine it with that entry, gives me 2. And then I do 2 times 4 to mix it with the other entry. That gives me 4. So now I'm done with the second row. I'm completely done. There's no other way to mix and match. So I built the matrix. Great. So now what is the next step? Well, the next step is reducing. Now the reducing is the step that requires just a little bit of addition and a little bit of shifting things around. But that's where the magic happens, in the reduction step. So the way that we reduce this thing, I'm going to go ahead and put these parentheses here because it's going to be another matrix, is when we're building this matrix, since we're doing it in such an orderly fashion, some of these entries in here have the same quote-unquote dimension, meaning that they are the same in size. So a good way to think of these entries in the matrix, or you can think of it as cubby holes. And so this is the biggest cubby hole here, these cubby holes on this anti-diagonal have the same size. They're actually in the tens place. And this cubby hole is the smallest here. So in the matrix, everything that falls on what we call an anti-diagonal is the same size. So you add those together. You put them in the same cubby hole. Instead of leaving this one up here separate from this one, you combine them all in this bottom one. So if this was a bigger matrix, as you can imagine, like building and multiplying bigger numbers together, anything that falls on a diagonal, an anti-diagonal, is the same dimension just based off the way that you build it. So we're doing 2 times 2, 2 plus 2. If we add those together, that equals 4 there. So you're basically pushing this 2 into there, and so you end up getting a 4 there. So I'm going to go ahead and put 4 here. And I just leave the 1 there because it's there. And I leave the 4 here. So what happens to this spot? Well, I moved this 2. I took 2 out that cubby hole and I put them in this cubby hole. So I'm left with 0 in that cubby hole. So there you go. And now the last step is to just write down your answer. Just like that. And the beauty about this is the fact that the matrices is already organized for you. It's organized along this L, this down and right. So the biggest number here is at the top, and it goes down in order. So that's the 100, the tens, and the 1 place. And so that matrix here, actually, I don't need these parentheses, but it just becomes 144. And that's your answer. So you just write it down already in order. And no matter how big your matrix is, it's always going to be along that line. So a couple key things to remember is that the entries in here, you want them to be between 0 and 9. If they're big, you'll have to shuffle them around and put them into the next entry. And I'll do an example that actually you have to do that. Okay, so there's one example, 12 times 12. So very nice on that line. So let's do a few more of these. Okay. So let me get another piece of paper to make it easy to see. All right. Now let's look at something that doesn't have the same size. Let's look at something like let's say 5 times 25. We'll still stick with some easier examples here. So 5, it doesn't have a tens place, but it has a ones place. So in the tens place, I'm going to put a 0. And then I'll put a 5 for the ones when I write it down. That's the first step. Write it down as a row. And the next number has a 2 and a 5 vertically. So I wrote those down, and now I can start to build the matrix. So that's the row, and that's the column. Now I got to build. So remember, we're building. We just do row by row. So the first row is 0 times 2, which is 0. And then the next entry of the first row is 0 times 5, which is also a 0. And then I have, for the second row, 5 times 2, which is 10. And then the last entry of the second row is 5 times 5, which is 25. Okay, so that's the matrix. So now the next step is to reduce the matrix, as we talked about. So we reduce this guy by looking at the anti-diagonal, like I talked about. And the beauty about this one is it's already reduced along that diagonal. 0 plus 10, there's nothing to move down here. It's already reduced there. So that's great. So the only thing that needs to be reduced is the fact that there's too much stuff in these cubby holes. Now, this cubby hole, you want it to be 0 through 9, all through here. The top one can be as big as it wants. But these, anyone that's along, that's not the very top left, needs to be 0 through 9. So here, there's 25 here. So there's 20 too many in this cubby hole. So 20 would actually be a 2 if I just moved it here, because this is a tens place. So I'm just going to basically, I'm going to circle the 5 because that's what's going to be left over. And then I'm going to take the 2, which really is 20, I'm going to push that over into this cubby hole. So I'm going to get rid of those 2 and I'm going to add it to that 10. So that's going to make 12 now. So I circled a 5. So you always work from the bottom right going across and up. That's how you do this reduction. But now you see I have 12, which is also too big for that cubby hole. It's 10 too many. So I'm going to circle the 2 because that's what's going to be left over. And then I'm going to get rid of that 1 and push it over here to where that 0 is. So now that's going to be 1. So when I write down what I have left, I got a 1 there. I have a 2 because I circled it there, remember? And then I have a 5 left over. And there's a 0 there. And so it's reduced. And so now I just write down that answer, which is 125, exactly as what we expected. So, okay, I hope that wasn't too hard to understand. But, okay, let's go through, do a bigger number as the final example. And if you're still with me, afterwards I'll post another video doing a few more examples before I go into a lot of detail. So let's look at something bigger. How about this? Let's look at, I'm just going to write down any number. 274 times 326. I mean, this is going to be kind of a big and nasty one, right? So you think. So we got a 3 by 3 here. And so I'm going to write first 2, 7, and 4. And then I'm going to do 3, 2, 6. All right, now I'm going to start building this guy. And the great thing about building it is you kind of already know what the structure is going to look like, because I know I'm going to have 3 rows and I'm going to have 3 columns, because I have 3 entries in both of them. All right, so I start building my first row. 2 times 3 is 6. 2 times 2 is 4. 2 times 6 is 12. Then I start building a second. 7 times 3 is 21. 7 times 2 is 14. 7 times 6 is 42. Then I do the third row. 4 times 3 is 12. 4 times 2 is 8. 4 times 6 is 24. All right, that's the building part. Now I got to start reducing. So reducing, I look at these anti-diagonals. So there's a diagonal there that crosses. Then I got a diagonal here. And then I got a diagonal here. So everything along those diagonals I add together in my reduction step, the first part of my reduction step. So let's go ahead and do that. Let's start adding these guys. So 6 is still there because it's not being changed. But I got to bring that 4, add it to 21. So 4 plus 21 is 25. And now that becomes a 0. And then I got to do 12 plus 14. That's 26. And then I got to do 26 plus 12, which is 38. So I have a 38 down here because I pushed all those down that way. So then that's a 0 and a 0. You see what I did here? I'm moving all these down into that one cubbyhole because they're all the same size, meaning the same dimension. I'll go over that in more detail later. But 12 plus 14 plus 12, 38. Now, I have to do 42 plus 8, and that gives me 50 in that one. And this is a 0. And then I have the 24 here because it's by itself. So now is the next part of the reduction step, which is these are too big for their cubby holes. You know, these are double digits and they need to be single digits. So I need to start shifting some things around, right? Just like we talked about. So with this one, what I'm going to do is, again, I circle the 4, the 2 goes to this guy, and that becomes 52. Then I circle the 2, and then the 5 goes to this one. So 38 plus 5 is 43. And then I get rid of that because I already added it. And now I circle the 3. And now I have a 4 here that's too big. So the 4 goes and adds to the 25. So 4 plus 25 is 29. So I'll cross that out now, and I got 3 here. So now this 25 is 29, but it's still too big. So I circle the 9 because that's what's going to be left over, and I have to add 6 and 2 together. So that's going to give me 8. So I'll cross these guys out. And so what am I left with? I'm left with 8. Let me slide this up so you can see it. I'm left with 8, 9, 3, 2, 4. And so that means the answer for that is 8,900. Let's see, 3, 2, 4. Whoops. 89,324. Now, normally, that would be a mess to try to do this with the line method, or to also do this with a lot of the other typical methods. And this is just really just shifting numbers around in the correct cubby holes and adding. So it's something that can be done by people who don't even have, I would say, a very wide base of mathematical training. So I find this very fascinating that, you know, just shifting things around in a matrix makes multiplication pretty intuitive and very ordered. And the great thing about this too, especially once you understand why this kind of machinery works, is that this will make it easier when you get into more advanced subjects. You'll have a more intuitive feel as to what you're doing when you're manipulating and using matrices to do more complex things. And so let's check to make sure that I didn't goof up on this. I'm going to use a little separate calculator here. So I did 274 times 326, and I got 89,324, which is exactly what I got here when I use this method. So this does work. I'll do more examples that aren't, quote unquote symmetric, meaning like, 3 digits times 3 digits. This works if you do, any number of digits, like a 2-digit number times a 3-digit, or, a 4-digit number times, it doesn't matter. This method will always work. You just gotta follow these simple rules, and I'll show some more in later videos if that's what you guys would like to see. So I hope this is helpful, and I think it could be very useful for a lot of people, and look forward to your feedback. Thank you.